So we are going to discuss about questions which can be reduced to exact differential equations. So sometimes a differential equation which is not exact may become exact on multiplication by a suitable function, the so-called integrating factor. So we'll discuss a few examples of differential equations which are not exact but can be transformed into exact form by suitable integrating factors. So let's start by defining a suitable or special integrating factor that can convert a non-exact differential equation into exact differential equation. So if a differential equation m dx plus n dy equals to 0, it's not exact in a domain D, but the differential equation becomes exact after multiplying by a function mu of xy, then this function is called an integrating factor of the differential equation. So for example, consider the equation 3x squared, 3y plus 4xy squared dx plus 2x plus 3x squared y dy equals to 0. So here, m is 3y plus 4xy squared, and n is given by 2x plus 3x squared y. Now the test for exactness is that we have to find partial m partial y. And in this case, partial m partial y will be given by 3 plus 8xy. And then partial n partial x will give us 2 plus 6xy. Now, clearly, we see that partial m partial y, whose value is 3 plus 8xy, is not the same as 2 plus 6xy, which defines the value of n dx. So if I call this equation 1, so this means that equation 1 is not exact. So that given differential equation in that form is not exact. But if we let a function mu of xy be defined by x squared y multiplying by equation 1, we get, so we are getting x squared y, we multiply by 3y plus 4x y squared dx plus 2x plus 3x squared y dy gives 3x squared y squared plus 4x power 3 y power 3 dx plus 2x power 3y plus 3x power 4y squared dy equals to 0. So which will be now our new m becomes 3x squared y squared plus 4x cubed y cubed. N becomes 2x cubed y plus 3x power 4y squared. And from this new m partial y gives us 6x squared y plus 12x cubed dy squared. Partial n partial x will be 6x squared y plus 12x cubed y squared. Now, in this now new case, partial m partial y, which is 6x squared y plus 12x cubed y squared, is the same as partial n partial x. So now the equation becomes exact. So this given function that made the equation to be exact is now an integrating factor. So the question will be, how do we find this mu of xy? How do we find this special integrating factor? So there are different ways of defining this mu of xy. So rule one, if partial m partial y minus partial n partial x, if you divide this by n, is a function of x alone, then mu of xy is given by e raised power the integral of f of x dx, where f of x is this quotient. So for example, solve 2x log x minus xy dx plus 2y dy equals to 0. Okay, so this is given as dy. The first one is given as dy, the second one is given as dx. So here, if this is the structure of the equation, m dx plus n dy equals to 0, then m will be 2y and n will be given by 2x log of x minus xy as given in the equation. Then let's try to see whether this is exact or not exact. So partial m partial y will give us 2. Partial n partial x will be. Now here we use, the first one, we use integration by differentiation by product rule. So if we let this to be u, this to be v, u prime will be 2, and then log of x, plus, if you differentiate this, you get 1 over x, multiplied by this, you get 2, and then differentiating this part, you get minus y. So which you can write it as 2 into log of x plus 1, and then minus y. So clearly, partial m, partial y is not the same as partial n, partial x. So which means that this equation is not exact. But then let's see, partial m, partial y minus partial n, partial x divided by n will give us partial m, partial y is 2, minus partial n, partial x is 2 log of x plus 2 minus y. And then if I divide by n, I'll have 2x log of x minus xy. So I'll have 2 minus 2 log. So this is what I'm going to call f. X minus 2 plus y, because minus is positive, divided by 2x log x minus xy. Now, f will be 2 minus 2 is 0. So I'll have y minus 2 log x divided by 2x log of x minus xy, which can be written as minus 2 log x minus y divided by factor out x into 2 log x minus y. And we find that this bracket and this bracket are equal, and so they cross each other. So f becomes minus 1 over x, which is just a function of x. So therefore now mu will be given by e raised power the integral of f of x dx. So e raised power negative integral of negative 1 over x dx. And this is the same as e raised power negative ln of x or log of x. So mu will be e raised power ln of x power negative 1 using properties of logs, which is just the same as x power negative 1, which is the same as 1 over x. So on multiplying the original equation by 1 over x, we get 1 over x into 2x log of x minus xy dy plus 2y dx equals to 0. So the first will give us 2 log of x minus y dy plus 2y over x dx equals to 0. So here now, m is 2y over x, and n is given by 2 log x minus y. So partial m, partial y will be 2 over x, and partial n, partial x will be 2 over x. So then, which implies that partial m, partial y is partial n partial x, which is 2 over x. So the new equation is exact and can be solved by the previous methods on solving exact differential equation. To get that the solution will be 2y log of x minus a half y squared equals to c. Log of x, almost. And then the last case, rule number 2. So please check this solution by following the same steps in the previous classes. So rule 2, if you have if m is of the form, or if simply you are given that the difference between these partial derivatives of m and n divided by m is a function of y only, say f of y, then mu is given by e power the integral of f of y dy. E.g., if we have the equation y power 4 plus 2y dx plus xy cubed plus 2y power 4 minus 4x dy equals to 0, we see that m is y power 4 plus 2y, so which means partial m partial y is 4y power 3 plus 2. N is given by x y cubed plus 2y power 4 minus 4x, which means partial n partial x will be y power 3 minus 4. And it's very clear that partial m partial y is not the same as partial n partial x. So our equation is not exact. But if we find out this difference, partial m partial y minus partial n partial x is 4y cubed plus 2 minus y cubed minus 4, which will give us 4y cubed plus 2 minus y cubed plus 4. So this will give us 4y cubed minus y cubed is 3y cubed 2 plus 4 is 6. So you can factor out 3y cubed plus 2. Now, when you divide this by m, we have 3y cubed plus 2. And you see m, if we factor out y, we get y into y cubed plus 2. So this reduces to 3 over y. So which is purely a function of y. So therefore, the mu will be given by e raised to the integral of 3 over y dy, which is e raised to power 3 ln of y, which is e raised to power ln of y cubed, which is just y power 3. So therefore, the suitable integrating factor in this case will be given by so remember in the definition here we have this will be partial m. In the definition here, this should be partial n. So you subtract partial n partial x from partial n partial x from partial m partial y. So the order is different from the first case where we're starting with m. So this difference now so this simply you subtract. So this is the one that has a negative sign. This is the plus. So this plus, this minus. So this is simply partial n partial x minus partial m partial y will be given by y cubed minus 4 minus 4y cubed plus 2. So which will be y cubed minus 4 minus 4y cubed minus 2. So you get minus 3y3 minus 6. So when you factor out minus 3, you get y cubed plus 2. And then taking partial n, partial x minus partial m, partial y divided by m will be minus 3y cubed plus 2. M from this is y power 4 plus 2y, which will be minus 3y cubed plus 2 over y into y cubed plus 2. And this gives us minus 3 over y. So mu is e raised to the integral of minus 3 over y dy, which is e raised to power minus 3 ln of y, which is e raised to power ln of y power minus 3, which is the same as y power minus 3, which is 1 over y power 3. So multiplying the original equation by 1 over y cubed, we have 1 over y cubed into the equation was y power 4 plus 2y dx plus x y cubed plus 2y power 4 minus 4x dy equals to 0. So this by this will give us y. This by this will give us 2 over y squared dx plus this will give us x plus 2y minus 4x over y power 3 dy equals to 0. So our new m is y plus 2y squared. Our new n is x plus 2y minus 4x over y cubed, from which partial m partial y is 1 plus minus. So remember, this can be written as 2y minus 2. So when I drop, I get 4y power 3. So 1 minus 4y power 3. And this will give me partial m, partial n, partial x to be 1. This doesn't have an x, so this other will give me minus 4 over y power 3. And you see now, in this new equation, partial m, partial y, which is 1 minus 4 over y power 3, is the same as partial m, n, or x, which is exact. So once we have actually gotten an exact differential equation, so this new equation is exact. And so you solve this new equation by the previous methods discussed to get the solution. So we can solve following the previous methods discussed. And in this case, if you solve that, you will get x into y plus 2 over y squared plus y squared equals to c. So that is how sometimes you can convert a non-exact differential equation to exact differential equation and then solve.